I have Maximilian Nägele. Is that...
That's quite good, actually.
Okay, well, I'm Dutch, so I should at least know a little bit of German. Anyway, we have Maximilian talking about optimizing ZX diagrams with deep reinforcement learning. So please take it away.
Yeah, thank you for the invitation to the seminar. Yeah, this work was done together with my supervisor, Florian Marquardt, the last few months. Let's jump right in. So here on this slide, I just copy-pasted for you some papers about ZX calculus, which were published the last few years, let's say, and they fall broadly into two categories. All of those, they are about circuit optimization, and this is a bit of an outsider. This one is about speeding up quantum circuit simulations using tensor networks. And we have even two more categories. These papers here, they use some deterministic handcrafted algorithm to achieve their goal, while these two papers here, they use simulated annealing, which is some general probabilistic optimization strategy to solve discrete optimization problems, let's say. But really what all of them have in common is that they try to optimize a scalar quantity of ZX diagrams via repeated application of ZX transformation rules. And for circuit optimization, this would then, of course, be gate count or 2-qubit gate count. And for these tensor network simulations, this would be some graph property called tree width. But this framework of repeatedly applying actions or transformations to optimize a scalar quantity is exactly also the framework where reinforcement learning can always be applied. So let's go back to the title of this talk. And I want to quickly tell you already what I mean with each word here. So ZX diagrams, I think I don't need to tell you anything about, and also I will not. I hope you already know them. With optimizing, as I said, could in principle be any scalar quantity that we can compute from the ZX diagram. In our case, we will not do circuit optimization or tensor network simulation yet. Instead, we choose kind of a proof of principle example by reducing the node number of ZX diagrams. With deep, I mean that the policy that actually in the end will optimize that ZX diagrams is encoded in a deep neural network. Specifically for us, it's going to be a graph neural network, which is a special kind of deep neural network. And then reinforcement learning is just the algorithm we use to train this deep neural network to perform the optimization better and better as training progresses. So the outline of this talk is closely going to follow the title. So first I want to tell you what is reinforcement learning, specifically policy methods. Then I want to introduce to you graph neural networks really from scratch. Then finally, I want to tell you how can we encode all these different rewrite rules that we have in ZX calculus in actions that can be applied by a reinforcement learning agent. And then we are finally ready to look at a result and see how does the learn policy of our agent compare also to, let's say, a handcrafted simple deterministic greedy strategy and also simulated annealing. Then finally, we were curious and wanted to understand even better how local, for example, is the policy our agent learns and how good is it to known optimal policies. And finally, I want to just quickly summarize what we learned and give you an outlook. And I think we are not so many people, so I think feel really free to interrupt me at any time, especially in this first part where I kind of lay the foundations for this talk. I think it's much more important that you understand what I'm saying than that I can finish everything that I've planned here. Okay, let's start with reinforcement learning. So we have a ZX diagram. Let me use this picture quickly to introduce my notation. So my spiders, they are white and gray. We have Z spiders and X spiders. We have Hadamard gates, and there are some angles on my spiders. And now I give this ZX diagram to my reinforcement learning agent, and this agent, it will tell me what should I do with it to achieve my goal. For example, it could tell me, yeah, at this step, please fuse nodes number 3 and 5 together. And this whole process then gets repeated iteratively, either for a fixed amount of steps or until the agent says, okay, I cannot simplify this diagram any further. Let's stop. Then after, yeah, as I said, this action is applied, and then we repeat this over and over. And now I also want to teach you, let's say, the lingo of reinforcement learning. So the thing, in our case, the ZX diagram that we give to the agent, it's always called an observation. The agent then tells us what he wants to do to the observation. We are in action, and the environment is basically a container, in our case, for the ZX diagram, and it has even an additional job. In addition to providing the observation, it also provides, after each action application, a scalar number, which is the reward at each time step. And you should understand the reward kind of as telling you how much closer did you get to your optimization goal by applying this action. And now really the goal of reinforcement learning is to, okay, I will read it, optimize the expected value of the cumulative reward in a trajectory. Now first, what is a trajectory? A trajectory is just the repeated application of actions to the diagram until the optimization finishes. The cumulative reward is exactly the sum of all the rewards that occur during the trajectory. And it's important that we really optimize for the sum and not just at each step for the highest immediate reward. Because if we optimize for the sum, this means that at one step I can maybe even have a negative reward if this then later allows me to reap the benefits, so to say, and get huge positive rewards during the rest of the trajectory. And now, what do I mean with expected value? Well, first, the policy of our agent is going to be probabilistic, so this expectation value goes over that. And then even our environment can be probabilistic. In our case, the start state of our environment is going to be probabilistic, because we want to teach the agent to simplify not only one specific ZX diagram, but all ZX diagrams. So this is what this expectation value is taken of. Okay, this is the general framework for reinforcement learning. And now let's have a closer look at what are policy methods and what is actually inside this agent. So as I told you, at each time step, the agent gets an observation. I denote here as OT. And for policy methods, the agent is just going to be some function f. This I will call the policy of the agent, this function. And this function takes as an input the observation that was provided, and it gives as an output a table of probabilities for each possible action that could be applied to the diagram. And what is important, this function has some parameters, some free parameters with respect to it is differentiable that we can optimize over. Okay, and now the general scheme goes on. We sample an action, we apply it, we get a reward, and we do this many times until one trajectory finishes, and then we even do this for many trajectories and different starting ZX diagrams. And this whole process would then be called, let's say, the sampling phase of our policy method training algorithm. And then we take all of these experiences that we recorded, and we start a training phase. And during the training phase, what we roughly do is we calculate first the cumulative reward for each trajectory, because this is kind of the value we want to optimize, right? And then there's a very clever method, which I cannot explain you in detail, to from this then directly estimate the gradients of our expected cumulative reward. This is what we want to optimize for, with respect to already the free parameters of the function of the agent. And then we can really just perform gradient descent with respect to this cumulative reward of our parameters. So we calculate this gradient, we take a small step in its direction. Our policy is hopefully now a little bit better. We go back to the sampling phase, we sample some more experiences. We go back to the training phase, we again do one more gradient descent step, and our policy just improves and improves over time until hopefully we converge to some local, or if we are lucky, global minimum, where the agent then has a useful policy. Okay, and now so far I just gave you this f here, which is this black box differentiable function. So let's have a look what should this f actually be. So for complex, deep reinforcement learning tasks, this f is usually a neural network, also in our case. And usually the simplest idea would be to use a dense neural network, which will not work for us, but I still want to quickly introduce to you what it is, because it will be later also a building block of graph neural networks. So a dense neural network, the simplest version of a dense neural network just looks like this. It has an input, a vector x, with a fixed dimension. In this case, it's dimension 3, and it just has 3 numbers. You can think about these circles here, each being a number. And to compute the output of our dense neural network, we just take this vector x times a matrix and add this bias vector b. And finally, because we don't want to be able to only have linear transformations, we apply some element-wise activation function, which I just call GE here, which should be nonlinear. We, for example, use the tangents hyperbolicus. And now this structure is not very expressive yet because we just have this linear function and then once the nonlinear function. So what you usually do to make this more expressive is you just add another layer. So this is called now the hidden layer in the middle. You can compute the values of the hidden layer in exactly the same way I showed to you before from the input layer. And then in the next step, you can calculate the output layer from the hidden layer. And the trainable parameters here would then, of course, be all the entries of the weight matrices and of the bias vectors. And if you make this hidden layer big enough, in principle, you can learn any function you want to. But these dense neural networks, they're very powerful, but for our case, they have 2 big problems, which is the input and the output size of them is fixed. But we want to optimize the node number of ZX diagrams, so the size is going to change. Of course, now the maybe naive way would be to say, okay, we only consider ZX diagrams up to a maximum size and we pad them with zeros wherever there are actually no nodes in our enumeration of our features. But that would lead to another problem, which is that these dense neural networks, they don't make use of this already very nice local structure that ZX diagrams have. And for most optimization goals, we would really expect our optimal policy to depend only on some local neighborhood around the place where the action that we want to apply is actually done. So if I apply an action at one point of the diagram, it should not depend on the node features very far away, let's say. And graph neural networks, they can solve both of these problems, and that's why we would expect when using them to have much faster training and also to be able to generalize much better to unseen examples of ZX diagrams. Yeah, so we don't want to use dense neural networks, we want to use graph neural networks for our policy. Now let me try to explain what a graph neural network is. There will be some equations, but please bear with me. So a graph neural network, it takes as an input not a vector, but directly a graph. And what I mean with a graph is some nodes connected by some edges, and each node, it can have a feature vector. Now this is actually just a vector describing this node. For ZX diagram, this X vector, for example, could describe, is this a Z spider or an X spider? And it could describe the angle of the node. And also in principle, each edge could also have an edge feature vector. For ZX diagrams, maybe it's not needed, but let's say, for example, I have normal edges or Hadamard edges, then I could use this to distinguish those 2 kinds of edges. And now our goal is to iteratively update these node feature vectors via some differentiable manner with a fixed amount of trainable parameters that does not depend on the structure and the size of the diagram at all. So this is gonna happen in a few steps, and I want to focus first now on how I would update the state of this node xi, and then for all others it's the same. So first I will need something called the message network, and this is just some differentiable function with some trainable parameter theta here indicated, and it takes as an input the node feature vector. Yeah, I'm not writing the vector symbols anymore, but these are all vectors. Then a node feature vector, a node feature vector of one of its neighbors and also the feature vector of the edge connecting it. In our case, this is just going to be a very simple dense neural network where all of these feature vectors here are concatenated on top of each other to form one big input vector. And then this function will also give us a vector of any size we desire as an output. And now we use this message network and apply it to each of the edges separately that is connected to the node that we want to update. Now the problem kind of is we don't know how many edges there are. So the size of all of these edges is unclear in advance. So we need to do a second step in our update, which is called the aggregation phase. And how we do this or how this is usually done, is you use some aggregation function. And in our case, the element-wise mean over all of these messages that were computed for these edges here. Another option would be to use here, for example, the sum. But the point is you have some function that takes as an input an arbitrary number of these messages that you computed before, and it gives you an output vector of fixed size independent of the amount of messages you had. Okay, so then you have this mi vector for my node xi, and it carries information about the local neighborhood of this graph. And then I can finally calculate my new node vector for node I, the node vector xi prime, by applying even a second differentiable function, again, a dense neural network, to the node vector, feature vector of node xi and this message that I computed before. And then, of course, I can use exactly these two neural networks to update the state of each of the nodes, not only of this node. Okay, then also I told you we can update the edge vectors. And this is much easier because each edge, it always has two neighbors, right? So updating the edge vectors just needs one additional differentiable function, again, a neural network, which takes as input the feature vectors of the connected nodes and its own old feature vector. And now what this graph neural networks allows us to do is we can basically compute or predict action vectors, or in our case already action probabilities for each node and each edge. So if we can identify each of the actions we want to apply to our diagram with either a unique edge or unique node, and we can predict action probabilities for them and thereby encode our policy. So let me quickly show you the complete scheme we have. We have a
Sorry, Maximilian, could you
yes.
ask a question about the previous stuff? So if you skip that new couple of things, yeah. So this node update function, so this doesn't take in the number of neighbors xi has, and the number of neighbors is also not encoded in the feature vector of the vertex, right? So how do you, like, how does it know about how many neighbors the vertex has?
This is actually, to be honest, I was asking myself the same question, and in hindsight, it might make sense to use the sum instead of the mean, right? Because then you could learn this. But now the question is, yeah, you're right. The answer is you're right, but somehow the agent still learns a non-trivial policy. That's my answer.
Okay. So it's like with every neural network, it's magic, essentially.
Yeah, but
Okay.
I think I still want to actually try to use the sum and see if it learns something better. Let's see.
Okay, thanks.
Okay, so the complete scheme would be I take a set X diagram, I feed it to my graph neural network, which is part of my agent. And this graph neural network then predicts action probabilities for each of my nodes and each of my edges. These are all the action types I have. I will explain them in more detail later. And because some of the actions, they cannot be applied always, for example, the fuse action, it can only fuse two spiders of the same color together, right? It cannot be applied here, so we need to artificially set its probability to 0, which means in reinforcement learning language that we mask this action. And then, okay, I was not very precise before. Actually, the output of the graph neural network is not probabilities, but unnormalized probabilities. So we write all of these vectors on top of each other, normalize them, then we have actual probabilities. We can sample an action and apply it to the diagram. And thereby we have our reinforcement learning cycle complete. And as I told you before already, we want to minimize the node number in the diagram. So as an instantaneous reward after each action, we choose the number of the nodes in the old diagram before we applied the action minus the number of nodes in the new diagram after action application. And clearly, if we sum all these rewards together, what we end up with is just the difference in nodes in the initial diagram minus the number of nodes in the final optimized diagram at the end of the trajectory. And I think now would again be a good time for questions about the general scheme, if you have any.
I have a question about the action.
Yes.
So when you said we identify each action with a node or an edge, I wonder when we talk about a ZX rule, it usually involves a node with its neighbors or a node with its incident edges. So how could you encode an action using the node and edge? Can you give me an example?
Yes, this will be the next slide.
Oh.
Okay, if there are no other questions, then let me just continue and answer this question. So these are all the actions we are implementing in our scheme. And let me go through them one by one. So the unfuse action is actually quite complicated because it actually exactly has this problem. We can identify, okay, easily the node that we want to unfuse, but we also need to choose a subset of the edges connected to it, and it's not clear how big that should be. So let me explain to you how we do this in detail later on the next slide and just go on to the next actions. So the fuse actions, also like I said, it actually involves two nodes, but this is still quite easily identified by just the edge connecting those two nodes. So we can identify it with a unique edge and don't need to do anything else anymore. Now the bialgebra rule let's start from the right to the left. It's also easily uniquely identified by a single edge. The other direction is actually, again, kind of a problem, but not so much because this diagram is completely symmetric in these four edges. So what we did, we just applied the bialgebra rule to the right direction if any of those edges were selected. Then we have also the color change rule, which is easily identifiable by a single node. And we actually only implemented it in this direction here from the left to the right, because together with the Hadamard identity action, it would otherwise be redundant. The pi action is also easily identifiable by a single edge, as well as the copy action in this direction. The action back again would be problematic because I would choose a set of nodes whose size is maybe not known before, and maybe they are not even connected. This could maybe be done. We did not do it in a similar way as the unfuse action that I will explain to you in the next slide. Then the Euler action and the Hadamard unfuse and fuse actions here, they are again easily identified by a single node. The identity actions here we apply automatically after each action application by the agent, just to make it a bit easier. And I also have this Hadamard loop action as an extra action that is applied all the time automatically, simply for implementation reasons, because in my program it's a bit annoying to have two edges connecting the same nodes. And this is the only way this pops up, because I also use the leg chopping rule to automatically remove redundant legs between spiders.
I have a question about the unfuse.
Yes,
the
the unfuse will also be more explained in the next slide, but
okay.
Maybe if you still have it, then let's discuss it after that. Okay, so how does the unfuse work? Let's say I want to unfuse the spider. So we introduce a new action of the agent, which is a node action, and it just says start unfusing the spiders and does basically nothing apart from making the agent kind of enter a kind of mini game where it only has two actions available. And the first of these actions is marking an edge. So selecting an edge, giving it an extra feature. And this it can do iteratively if it wants for all of the edges or for a subset of the edges, until it decides to select, instead of marking an edge, the stop unfuse action. And then what happens is the node actually gets unfused, and all the edges that were previously selected get connected to the new node. We don't split the angle yet. This could maybe in principle be done depending on how you want to do it with multiple stop unfuse actions that then correspond to angles that are put into the spider. Does this answer your question already?
No, the question that I wanted to ask was, you have alpha plus beta in the previous slide. So how do you
Yes.
decide what alpha and beta are? If, because it could be arbitrarily, like it's a continuous parameter, right?
Yes, okay. Then let's discuss this in more detail. So as I said, we don't implement this. Okay, if you really want to implement this, there's also continuous reinforcement learning. And then, of course, you could predict this with some continuous action, but it's probably not useful to make this continuous, right? Because mostly you care about, is this a multiple of pi half this angle, or is it some other random number that does not help me to apply any rules? So then you would probably more want to apply, define a discrete set of unfused actions, each corresponding to an angle that gets put into the newly created spider if you want to split up your angle. But we did not do it. And also for circuit optimization, I believe it's always clear a priori which angle you should put there. So you could just kind of fix this and not have to deal with it, I believe, in many cases.
Maximilian, there's also a question in the chat by Konstantinos. He asked, in a rule like Euler, where the middle of 3 nodes is selected, is it also checking the neighbors? Is the rule that is applied to 3 nodes or just 1 node?
Okay, so the Euler rule, as you say, it clearly acts on all of the nodes, but I uniquely identify it with the middle node. And if the nodes next to it, they don't have the right color to actually apply the Euler rule, and it's not allowed to even apply it, then I even mask it before the agent can even select it. That's this like artificial setting the probability to 0. Okay, seems like this answered the question.
Sorry, I have a question about the unfusing. So
Yes.
here you mark the edges that you mark 2 edges. How do you choose how many edges to mark? Or when you have a spider that has many edges, how do you determine the unfuse scope?
Yes, that's exactly. Okay, at this point here, after the agent selected the start unfuse action, the agent can only choose to either mark one of the edges. So for each of the edges, there's an action and an associated probability that the agent predicts. And the agent at each step also predicts a probability to choose the stop unfuse action. And then I just sample from this. And if the probability to mark edges is very high, I just mark them. And then at one point, the agent thinks, okay, let's stop. And then it will set the probability of the stop unfuse action very high. So in principle, it can learn to choose any subset of edges.
Oh, I see. Then who determined the probability of marking each edge?
That's the policy of the agent, the graphical network.
And that is determined before we run the deep reinforcement learning, or that's...
In the beginning, it's going to be random, and then we train it, and then hopefully it understands which edges are actually useful to mark in exactly the same way as it learns other actions.
Oh, and this is based on the reward that you obtain from the training, right?
Yes. So during the marking edges phase, let's say, there will be always 0 reward because the node number doesn't change. But then after that, of course, there will be some reward. And because we always optimize for the cumulative reward of the whole trajectory, this will also have an influence on the actions that mark the edges before. Okay. Thanks for the questions. Okay, then let's have a look at. I see there's another question in the chat. Actually, there is a discount rate, but I mean, what I said still holds. We have this discount rate. I just didn't discuss it because I think it's not important for the point of this talk. If you're interested in discussing, let's do it at the end. Okay, so now we understand actions. Let's see how we encode our ZX diagrams as observations. So we have these nodes, and all of the nodes, they have some angle feature, which can be, in our case, we just choose this a multiple of pi half, because these pi halves, they are kind of important to keep track of So you can determine which actions you can apply. And also an arbitrary angle alpha here, which is just a placeholder specifying, okay, this is any angle that we don't want to tell you, but it's probably not a multiple of pi half. And then there's also a no angle feature because Hadamard nodes, for example, they don't have an angle, right? The way we encode this is just with a one-hot encoding, which means the angle feature will always be a vector with all zeros and 1, 1, and the position of this one in this vector will just tell you which of this angle was it. And in a very similar way, we also have something that I call the color feature for each node. Each node can be a Z spider, an X spider, a Hadamard, and an input or an output, where the inputs and outputs are also just used for bookkeeping at the edges, at the otherwise unconnected edges here of the diagram. And now for training, we sample randomly diagrams of this kind here. Actually, they look always kind of like this, and I give you some intuition, not exactly how we sample them. So our training diagrams always have in the beginning between 10 and 15 spiders randomly chosen. Then we also randomly sample the colors of the spiders and the angles. We put some Hadamards in there. And then I also choose an edge probability from which I then really globally sample each possible edge in the diagram, such that each of my spiders will have an expected number of neighbors, let's say between 2 and 4. And this is just my heuristic to produce ZX diagrams that look like ZX diagrams you would see in some ZX paper.
So is this essentially a Erdos-Renyi random graph?
I don't know this name.
So you're saying every edge has equal probability of appearing, right?
Yes, apart from the edges connecting the Hadamards, of course, because they are fixed. But yes.
Oh, right. Yeah.
Apart from that,
yeah.
yes.
Yeah, so then in graph theory, that's usually called an Erdos-Renyi random graph.
Okay, thanks. Then that's what it is with the edge probability set, so that we don't have much too many neighbors or too few neighbors per node, let's say.
So the example you gave here is planar, but that's not like generally true then, right?
No, that's not always the case.
Yeah, okay.
Okay, now we understand everything. We know what are actions, observations, and reinforcement learning, so we can have a look at the results finally. So what I plot you here is the training process of the agent. On the x-axis, you can see the total actions the agent applied during training to some ZX diagram. And on the y-axis here, you can see the mean cumulative reward per trajectory. And we can see the random policy, which we start with, it's super bad. It actually increases the node number of the diagram by 30. While as training progresses, we actually reach the break-even point, and then I really learn also to reduce the node number of the diagrams. And after, let's say here around, I believe this is 10 million steps, the agent converges to some, for it, global or probably more local minimum. And this whole training process, so you have a rough idea, takes around 41 hours on one compute node with 2 GPUs and 32 CPUs in our case. And now, okay, the agent can simplify the diagram, but this could mean now everything, because maybe it just learned to always apply all possible fuse actions, and everybody could have directly written a deterministic code that can do the same. So we want to compare the agent also to 2 other strategies. And the first strategy is going to be a greedy strategy. That means we basically just always choose the action that reduces the node number the most in this specific case. And if there are only actions left that increase the node number, then we don't do anything anymore and we stop the optimization. And the second one is simulated annealing. That is just exactly this probabilistic general technique that's applied to a lot of problems for solving these discrete optimization problems. Okay, and then we do this by sampling 1,000 diagrams with 10 to 15 start spiders, so same size as our training set. And we compute the average number of nodes left after optimization through these 3 strategies. And we can see that the reinforcement learning agent is doing better than the other tools. And also simulated annealing is kind of competitive. but it needs a lot more steps in the environment due to its probabilistic nature of the optimization. In principle, if you increase this amount of steps further and further, you would expect simulated annealing to be the perfect strategy in the limit of steps going to infinity. So then you would also expect it to beat or at least be as good as the reinforcement learning agent. But of course, this is not possible in practical applications. And then I told you before, graph neural networks are so super great. We can put any input size and they generalize super well. So we also wanted to test this by now evaluating also the performance of the agent on diagrams that are 10 times bigger than he has seen any time during training. So we basically just repeat the same numerical experiment with diagrams that now have 100 to 150 star spiders. And we can see that the results are basically the same. The reinforcement learning agent is still very competitive compared to the other two strategies. And moreover, it's even faster. Of course, the training takes a lot of time, but once you're trained, you don't need to do it again. So the reinforcement learning agent takes only around 4 seconds to simplify one of these diagrams of this size, while simulated annealing with 20,000 steps already needs 40 seconds, and the greedy strategy even 100 seconds. As a small disclaimer, I should tell you that the reinforcement learning agent has access to a GPU to evaluate its neural network, and the other two strategies, they just need CPU. So it's not a completely fair comparison, maybe.
How did you tune the hyperparameters for the simulated annealing?
Yes, that's a good question. So basically, I took for each of the two example sizes one diagram that was quite hard to optimize by greedy, where greedy failed, and I needed many difficult steps, actions, let's say. And I optimized by hand hyperparameters of simulated annealing for this specific diagram. But then I kept it fixed over all of the 1,000 diagrams. So I did not optimize again hyperparameters for each diagram separately.
Konstantinos asks, did you also compare to physics?
No, but I think especially since our final node numbers are so small, I don't expect it to do very well, right? Because you always have at least one node connected to each input and output, and then you have Hadamard edges. So yeah, that's basically why I didn't do it.
Oh, right, because you count Hadamard edges as a node as well. Right?
Yes.
I see. Yeah. Do you have some examples for what kind of diagrams your thing produces?
Yes, actually, one final diagram will come later in 2 slides. I only have one in this presentation, though, I believe. Okay. Then let's go on. And now, okay, we saw some average figures here, but I actually want to show you also one optimization strategy, trajectory where I just took one diagram and optimized it with the reinforcement learning agent simulated annealing and the greedy strategy. And here we can see the number of nodes in the diagram versus the amount of steps I took the optimization steps I took. And of course, greedy at the beginning is very good, but then it plateaus because there are no actions left it can take. And then the reinforcement learning agent, I actually plot you here in opaque many different runs. We can see in the beginning it's very similar to greedy, but then it can gain an advantage by applying some rules that intermittently increase the cost or the number of nodes in the diagram, and thereby get to a lot lower number than the greedy strategy. And okay, the runs are a bit different because the policy of the agent is probabilistic, but on all of them it finds the same minimum on this exam. And now simulated annealing, it also works, but it's just a lot slower. So if you look at this inlay, simulated annealing also finds even the same minimum as the agent in the end, but it just needs a lot more time. And this is actually the diagram where I by hand optimized the hyperparameters for. So it's actually quite fast. It only needs like 1,000 to 2,000 steps, depending on the random seed of the simulated annealing. Okay, now we saw a trajectory, and now I will provide one of the optimized diagrams for you. So this is the diagram we saw already before. If you use a greedy strategy, you can basically only fuse these blue edges here, and you end up with this. This is also what the agent initially learns, but then it can simplify even further by first, for example, applying here the pi rule to this edge, and then later we'll also use the copy rule, and it will end up with something looking like this. Okay, and another example I was interested in is I just saw this diagram in some review paper, and I wanted to, as a human, it's quite clear. I think it's even your review paper, John, I'm not sure. As a human, it's quite clear how you would simplify it. You would just unfuse this node here, and then you apply the bi-algebra rule to those 4 nodes, and you end up with 1 node less than you started with. And I did not train the agent specifically on this. Probably this never even popped up in the training phase. But what the agent does, if I provided this diagram, is it also applies the bi-algebra rule, but in a very different way. It applies it in the other direction on this edge, first quite drastically increasing the nodes, and then it can fuse 2 times to some automatic like chopping and identity, and then actually it ends up with the same diagram. Okay, so now we saw.
Yeah, but if I can make a comment about this, so I think what your agent here discovered is that you never have to do the reverse bi-algebra, since by doing a forward bi-algebra and lag chopping and identity removal, you can always do a backwards bi-algebra. So you only ever have to do the forward one.
Yeah, I believe so too. Yeah. So if the lag, what you're saying, I think is if this lag was not there, it would still work the same way, right? And then, okay.
Yeah.
For me, this was not clear a priori, but it's yeah. Okay. Okay, now we saw some examples, but I think it would also. Do we still have how much time do we have left? Not so much, but okay, a bit. Now we saw some examples. But I also want to kind of come up with some more quantifiable ways to analyze the policy this agent learns. And for graph neural networks in general, it's kind of interesting in how local are the prediction it makes in the sense of how far away do features of the diagram still influence predictions at another point of the diagram. And how to do this is not so clear a priori, but we came up with one way, which I will try to explain you now. Okay, what we do is we take the trained agent and we simplify a lot of diagrams and always record which action was taken where with which diagram. And then we go back to each of these diagrams and we build it up in layers around the place where the action was taken. So let's say it was some node action, for example, a color change action. Then layer 0 would mean we just have the node where the action was selected on. And then layer 1 would be the node plus all of its nearest neighbors. And layer 2 would be then even, next nearest neighbors of the node and so on. And then we take the smaller sub-diagrams corresponding to layer 0, then a little bit layer 1 and so on. And we feed them, just them, not the rest of the diagram, to the graph neural network. And we see which action probability would the graph neural network now predict for the smaller diagram. And of course, as we add more and more layers, the action probability that it predicts should then actually be the action probability of the full diagram. What you can see here is already this probability of the increasingly bigger layers divided by the probability of this action being sampled in the full diagram where it was actually chosen for 4 different action types already averaged over 1,000 applications of this action. And okay, the main point of takeaway is that depends a bit on the action, but in principle, if we have next nearest neighbor information of our nodes, that's enough to predict, at least for the agent that we trained here, the policy it's gonna take. So we are still kind of quite local. We only go up to this layer 2. Okay, and then finally, as a second analyzation example, we wanted to consider a subclass of ZX diagrams where we as humans actually can quite easily predict the ideal policy and then compare this ideal policy to the policy that the agent actually learned by training on these random ZX diagrams. And the class I took is this class of ZX diagrams. So we have always a Z spider connected to this X spider, and we are interested in the probability of the copy action applied here. And the X spider, it has n output legs, and it has on n extra of those legs, we insert an additional Z spider with an angle alpha. And now if there are a lot of n extra spiders, makes sense to apply the copy action, because first, of course, we get rid of this, but we insert a lot of new Z spiders. But if there are a lot of n extra spiders, we can then in the next step fuse them together and get rid of the new copied spiders. But if there are no n extra spiders, does not make sense to do this copy action, because we get rid of only the X spiders, but we introduce a lot of new spiders that we cannot get rid of anymore. So the ideal policy here would be to apply the copy action if n out minus n extra is smaller or equal to 2. And we can see that, okay, we did not train the agent on exactly these diagrams, but just on the random diagrams, but it at least approximately captures this ideal policy in the sense that at least for n out up to 5, the probability of applying the copy action always is kind of 1 for the first 3 entries here, which corresponds to actually this ideal policy, and then it kind of sharply drops off. And for n equals to 6, we can see, okay, apparently this did not happen in the training, and also the interpolation is wrong. So for n extra equal to 3 and n out equal to 6, the agent would still apply this copy action, even though, okay, in this case, does not make sense to do it. So it's not perfect, but considering we didn't train specifically on this, also not too bad, I would say. Okay, so finally, I want to give you a quick outlook where this could go. And before I do that, let me advertise already next week's talk about reinforcement learning for quantum circuit optimization, right? That X calculus by Jan, I think he's also here, which already does part of this outlook, but the way they do their action encoding in their graphical network is quite different from us. So I don't think I'm taking anything away now from what will be talked about next week. So as you know, for circuit optimization, we have graph-like diagrams, and we have also quite different actions. So I just want to make the point that local completion is easily identifiable with one node. So it would really fit into our framework easily. And same goes for pivoting, which is easily identifiable by a single edge. So it could also easily be implemented in a similar way than what we did so far. And then there's, of course, also the neighbor unfusion rule, which is not exactly the same as the unfusion rule, because we have, again, this graph-like diagrams, but also choosing the subset of edges could kind of work in a similar way as we are doing it now already. And yeah, this neighbor unfusion rule, I think there was a talk by, I hope I pronounce this right, Callum Holker, and even a recent archive where he shows that introducing this neighbor unfusion rule before applying pivots or local completions can really help you in reducing your 2-qubit count. So it would be nice if we could do this also if we do reinforcement learning for that. What is still, to be honest, not 100% clear to me is the problem that this rule does not always preserve the flow, no matter whether G or C flow. And I believe in principle, probably the agent, we could train it to recognize if the rule is at least locally flow preserving, because these graphical networks, they're good in kind of recognizing or gathering local insights. But I think it's probably even impossible to train it to learn when the rule is only globally flow preserving. So this would be kind of a limitation, I guess. Okay, now finally, let me summarize with a recipe how to optimize the X diagrams with RL. Choose a goal and a reward that gets you there. Identify each of your actions with a node or edge. Then it's super natural to use graph neural networks to predict probabilities for all of your actions. You should mask the invalid actions, and then you can directly use any policy method of reinforcement learning to train your graph neural network and hopefully solve your optimization problem if you're lucky and chose the right hyperparameters of your optimization. With that, I'm done, and I think you can ask me questions now, and I'm warning you if you don't have enough questions for me. I also have some questions prepared I want to ask you.
I